Hello, today's our topic is static condensation. First we will discuss where do we use it, and let's give the definition. Is employed to reduce the number of degrees of freedom in an analysis. It is actually performing part of the solution before assembling the system of equations. Now, let's see what we really mean here. Okay, so for that, let's consider the following structure. Let's say that I have a simply supported beam here, and let's say that I put some spring at some point at the middle. Okay, and I want to represent the behavior of this structure with only 2 degrees of freedoms. Let me draw one more time. Defined at the ends of these at the end of member the continuous beam. Okay, so D1 and D2. And if we go back to our original structure, let's put 2 degrees of freedoms. I got D1 here, D2 here, and I also have D3 and D4. So in reality, this structure can only be solved with 4 degrees of freedoms, and we can determine the stiffness coefficients corresponding to these 4 degrees of freedom by using the classical approach. But here I want something different. I don't want to deal with the internal degrees of freedom here. All I want, what is the stiffness coefficient for this structure if I want to rotate that end by unit radians? How much moment do I need? And how much moment do I need to keep D2 equal to 0 when I have a unit rotation at D1? Okay, so I may have many different things here. I may have a truss members, I may have another beam, but right now what I want to do is to represent the behavior of all this complex structure in between with only these 2 D1 and D2 degrees of freedom. So how can I do that? How can I calculate the stiffness coefficients for D1 and D2? This is what we call the static condensation. So in other words, if you come back to our original structure, in the original case, there are 4 degrees of freedom, but I want to condense out the effect of these two and represent the behavior of this structure with only these two. This is what we call the static condensation. So how do we do that? But let's first write what we want. We want to reduce the degrees of freedom at the mid node. This is what we want, and represent the behavior of the whole structure D1 and D2. Okay, so this is what I want to do. All right, let's see how we can do it. First step. Now assemble the full stiffness matrix. Four by four full stiffness matrix. Okay, so in that case, I will have a 4 by 4 matrix, and let's label these. I want to condense out these two degrees of freedom to be condensed out, and I want to represent it with C. Okay, and this one and this one I want to retain them. I want to keep them, degrees of freedom, and I want to show it with R. Let me erase that, not with K, with R. Okay, now when you assemble the stiffness matrix, the first 2 degrees of freedom are the ones that I want to retain, and the other 3 and the 4th degrees of freedom are the ones that I want to condense out. So I will partition the stiffness matrix as follows. Here I have the stiffness coefficients for the retained degrees of freedoms. Here are the stiffness matrix for the condensed degrees of freedom, and I have the coupling terms here. Okay, and remember that this is 2 by 2. In this specific example, this is 2 by 2. Here I have the displacement corresponding to the retained degrees of freedoms, displacement corresponding to the condensed degrees of freedoms, and that's equal to forces, unbalanced forces applied to the retained degrees of freedoms and unbalanced forces applied to the condensed degrees of freedoms. Okay, so I have written the full stiffness matrix, full equilibrium equations for this structure, but I first number the ones that I want to keep and then numbers the ones that I want to condense out. I obtain the following stiffness matrix or the following equilibrium equations, and I can partition these equations into 2 parts. At the top I'll see the retained ones, and at the bottom I have the condensed ones. Okay, now let's do the multiplication. Row multiplied by the column should give me FR. So I have KRR multiplied by UR plus KRC multiplied by UC is equal to FR. That's my first equation. The second equation, I multiply this row with that column, and that should give me FC. So I have KCR multiplied by UR plus KCC multiplied by UC should give me FC. That's my second equation. Now let's write this equation in a different form. So I'll just say rewriting equation 2 in the following way. So I'll have U condensed is equal to minus Kcc inverse multiplied with Kcr times UR minus Fc. Okay, let's call this equation star. Now inserting equation star into equation 1 and rearranging the terms, I have the following equation. Now KRR minus KRC Kcc inverse KCR multiplied by UR, let's do this, is equal to FR minus KRC multiplied by Kcc inverse multiplied by Fc. Okay, so I obtained what I did is I just put UC into this here, okay, and I had UC obtained from the second equation, put it into that equation, rearrange the term, I obtained the following equation. Now what I see here is this will give me a new stiffness matrix, so I call it Kc, and this will be my condensed stiffness matrix. And if you take a look at this part, that will give me a new force vector Fc, and this is the condensed force vector. And my reduced or condensed equilibrium equation becomes are done as follows. This is a new stiffness matrix Kc multiplied by Ur is equal to a new force vector, and for this specific example this will be a 2 by 2 matrix. This is 2 by 1 vector, and if you think about it, this Kc is actually describes the behavior of this whole structure with only these 2 degrees of freedom, and whatever unbalanced force I have on these degrees of freedoms, they are transferred to these nodes as an equivalent unbalanced forces with the following equation. So if I do a full assembly, obtain these submatrices and perform this multiplication or this operation, I obtain the stiffness coefficients for these 2 degrees of freedom, and they describe whatever I have. I can have much more, okay, much more members, much more degrees of freedoms, but at the end of the day, when you perform these calculations, you describe the behavior of this whole structure with only these 2 degrees of freedoms. Okay, then once you solve that degrees of freedom, so once UR is obtained, the values of condensed degrees of freedoms can be obtained from equation star. This process is called recovery. Right? Now let's work on an example problem. Now let's say that I have this frame. These are fixed supports. This distance is 8 meters. That distance is 4 meters. I have a uniformly distributed load, 12 kilonewton per meter. And I have a point load here, which is equal to 10 kilonewtons. And I'm assuming axial rigidity in this frame. Now, what I want to calculate is just this. If I want to pull this structure in this direction, how much resistance will I get? That's the only question I have. I don't care about the rotational resistance or anything. The only thing that I want to do is this. I want to pull it, okay? And how much resistance this frame will give me. That's the only question I have. So let's see. Now I will do the discretization. That's the discrete structure. These are the nodes. Now, what I want to calculate is the resistance of this structure to translation in the horizontal direction. So that's, I will call D1. That's the retained degrees of freedom. But in addition to that, I have a rotational degrees of freedom here, D2, and the rotational degrees of freedom here, D3, okay? So these 2 degrees of freedoms will be the condensed degrees of freedoms. So that's why I first number this and then number the remaining degrees of freedoms. And when you assemble the stiffness matrix, this is the stiffness matrix, K is equal to EI over 8. 3, 3, 3, got 3 and 3 here, 12, 2, 2 and 12. That's the full stiffness matrix for the 3 degrees of freedom system. And the force vector is as follows. F is equal to, I got 10 and I got minus 64 and 64 as my unbalanced bending moments. Okay, now let's partition the stiffness matrix. So I will just retain only 1 degrees of freedom. So I will partition it as follows. And also partition the force vector. So this is my KRR matrix. This one is KRC. This one is KCR. And that one is KCC. This one is FR and this one is FC. Okay. Now let's take a look at this equation one more time. This will give me my new stiffness matrix and I have to calculate Kcc inverse. So let's write it down. Kcc is equal to EI over 8, 12, 2, 2 and 12. And if you calculate the inverse of it, Kcc inverse will be equal to 8 over EI, and I have 0. Should be plus 0.086 minus 0.014 minus 0.014 and 0.086. That's the inverse of the Kcc matrix. So let's write that equation, Kc equation now. Kc is equal to KRR minus KRC multiplied by Kcc inverse multiplied by KCR. Let me check. Yes. Okay. Now that's equal to, I have KRR is equal to EI over 8 multiplied by 3 minus EI over 8, 3 multiplied by 8 over EI, 0.86 minus 0.014, 0.086. Let me correct this one. That's equal to 0.086 and multiplied by EI over 8, 3 and 3. And if you calculate that, this portion, you will obtain as EI over 8, 1.286. And then we will obtain our Kc as equal to 1.714 over 8 EI. So what does it mean? Let's come back to our problem. Now if I want to pull this structure in this direction, okay, I have to apply this much of force for a unit displacement. Okay? Here, all the resistances to translation in this direction as rotations are all included in this stiffness coefficient. Okay, you want to pull this structure, okay, move this structure in this direction with a unit displacement. That's the force you should be applying. Okay, now take a look at this. Let's see the force vector now. I have this 12 kilonewton here and 10 kilonewton. Okay, let's modify the FC. What is the equivalent lateral force of these two loadings? Okay, of this 12 kilonewton gravity load and 10 kilonewton lateral load. Automatically, actually, you can know the answer. Forget about this 10. If I have this 12 kilonewton meter gravity load, now as you see, that's a symmetrical structure. That's a symmetrical loading. So this shouldn't give me any lateral translation, right? So the lateral translation should only be caused by this 10 kilonewtons. So when I condense this force vector, I should obtain 10 only. Okay, let's see if this approach is correct. So FC is equal to, let's take a look at the equation one more time. Fr minus this expression. So I got Fr minus KRC multiplied by Kcc inverse multiplied by FC. Okay, that's equal to 10 minus 3 multiplied by, I just cancel out these two. I'm not writing, this one will cancel out each other, so I will just have the coefficients. 0.086 minus 0.014 minus 0.014, 0.086, 6, and I'm multiplying this by minus 64 and plus 64. Okay, and if you evaluate that expression, this one, you will find that that's equal to 0. So my condensed force vector is equal to 10. So this is something that we expect, right? Let's repeat. We find out the stiffness coefficient in this direction. In other words, if I want to create a unit displacement in this direction, I have to apply this much of force. Now, but I have 12 kilonewton vertical force and 10 kilonewton lateral force applied to that structure. So I'm trying to figure out what is the equivalent lateral loads of these two that will move this structure towards in the lateral direction. Now, the structure is symmetrical, okay? And I got 12 kilonewtons here, and I know that this 12 kilonewton doesn't create any lateral translation. So the effect of 12 as a force in the lateral direction is 0. It doesn't move the structure towards right or left. The only thing that will move the structure in the lateral direction is this 10 kilonewton. So the condensed force vector should be equal to 10. And as you see, this is what we obtained. And with this approach, I converted this structure into equivalent single degree of freedom system. Right? And I can just show that system as follows. I have a spring here, right, that resists the lateral translation, and I applied 10 kilonewtons at the tip of that spring, and the spring coefficient Ks will be equal to 1.714 divided by 8 EI. And from that you can calculate your displacement, the lateral deflection, and using the recovery phase, right, using this equation, you can then calculate the rotations, D2 and D3. So that's it. This is what we call the static condensation. But sometimes when we have larger structure, it is difficult to make this type of calculations. It's computationally very expensive. Numerically, we really don't want to take inversion because it's very costly. So there's an alternative way, and the alternative way is very straightforward actually. It is, we do incomplete static condensation, okay, and from the incomplete static condensation we can obtain the equivalent stiffness matrix and equivalent nodal forces, okay. So as an alternative approach, is incomplete factorization and I will show you how. Again, let's take the same structure, right, this is 8 meters, this is 4 meters. I have a uniform distributed load here and 10 kilonewtons here. So I will do the discretization again. This time I will number it differently. I will keep first number the ones that I want to condense. That's D1, that's D2, and then I'll have D3. So in that case, these are the ones that I want to condense out. And this one I want to retain. And when I calculate the stiffness matrix, so K will be equal to 12, 2, 3, 2, 12, 3, and I got 3, 3, 3 multiplied by EI over 8. And my force vector is minus 64 plus 64 and 10. Okay? Now let's do Gauss elimination now. So let me rewrite these matrices one more time. 12, 2, 3, 2, 12, 3, 3, 3, and 3. I have EI over 8 here, multiplied by U will give me the force vector, which is equal to minus 64, 64, and 10. Okay? Now remember, in Gauss elimination, what we try to do is make these lower triangular coefficients equal to 0 by performing row and row operations. Okay? So my first row operation is I will multiply the first row and add it to the second row multiplied by minus 1 over 6, right? We'll make that coefficient equal to 0. And then again, I will multiply this row with this one. Sorry, multiply the top row with minus 1 over 4 and add it to the bottom row, which will make this coefficient equal to 0. So when you do the first step, my matrix looks like this: 12, 2, 3, 0, 11.667, 2.5, 0, 2.5, and 2.25 multiplied by EI over 8 times U. I should do the same thing, right? You do the same thing to this force vector. And our final force vector will be as follows: minus 64, 74.667, and I got 26 here. Okay, now if you think about it, now I uncoupled the first degrees of freedom from the remaining of the structure, right? I have zeros, so in other words, having a rotation here doesn't influence these coefficients. They are uncoupled, but I want to uncouple the second degrees of freedom also. So I will do one more step of Gauss elimination. This time I will multiply the second row with minus 2.5 divided by 11.667 and add it to the third row. Okay, and do the same thing here. And our final matrix is as follows: 12, 2, 3, 11.667, 2.5. I got 0 here, 0, and 0 here now. And this one is 1.714 multiplied by EI over 8 times U is equal to minus 64, 74.667, and 10. So as you see, This is the stiffness coefficient that I'm looking for. It is now uncoupled from the first and the second degrees of freedoms. And this is the equivalent force vector. And if you write down your third equilibrium equation, you multiply this with the force vector, it should give you, multiply this with the displacement vector, it should give you 10. So let's write it down. 1.714 over 8 EI multiplied by D3 should give us 10. And this is our equilibrium equation. And as if you think about it, this is my Kcc matrix condensed stiffness, and this is the Fc vector. Now you can argue that the first approach, doing these calculations, is easier. Yes, if you have a smaller matrix, if you are using a matrix operation tool, performing this is easier. But when the structures become larger, you have many degrees of freedoms. Of course, we handle these structures with computer software. And if you want to do static condensation, that's the procedure that we usually utilize. We do incomplete Gauss elimination. We condense out the ones that we want to condense, and we stop at this point, and this remaining portion of the stiffness matrix is our stiffness matrix that we were looking for.